When you like celebrity competition, and today we have John Green finish off.
Is that a yes? Start. We'll have to consider it. Okay, guys. Good morning, everybody. Happy Friday. There was a couple of folks that did not get their lab sheet back yesterday because I passed them out at the end. We'll try here today. If you want to pick it up, please yell. Juan, Heather, Nathan, Rachel,
Here.
Hunter, here, Brendan, here, Christopher, here, Dominique,
Here.
Kelsey, Olivia,
Which one? Sorry.
Okay, guys, quiz on Monday. Alkene reactions, including nomenclature, easy terminology, stereogenic alkenes, all that from the nomenclature. Okay, we have two outlines. One you printed, one I handed out. We're looking at the enantiomers of 1-bromo, 1-chloroethane. Is that right? Let's draw those again. We had them on the board at the end. Pretty sure I had something up like this. This was probably alkyl. What was straight up?
The bromine.
Bromine was straight up and plain. I think chlorine was forward. Chlorine was forward?
Yes.
This way, like this. And the H is thus going back. We can draw a mirror image of that. Okay, like it's looking in the mirror. What does it see? It's going to see that way, chlorine forward, H back, and the bromine up. Okay. Are those mirror images? Yes, they look like they're mirror images. Question of, are they the same or different? Are they the same or different? Everything's got a mirror image except a vampire. Is it the same or different? Okay. The mirror image of this clip is this. Same or different? They're the same. What about these two molecules? The mirror image, okay, bromine, bromine red, I reckon, black this way. Chlorine forward, so that's that one. If this is mirroring, it's going to be red up, green forward. There we go. Are those mirroring? This looks in the mirror, we'll see that. Green forward, gray back, black away, red up. Those are mirroring. Same or different? Well, how can we tell? Are they superimposable? Now this is really hard to be superimposable or stackable. But if we could take this and if it was sort of semi-invisible or hollow, we could just put it right on top of that one and it would just match up directly. Saucers in your cupboard, they just stack on each other because they're all just superimposable. Can we stack these right on top of each other? Well, boom, there you go. The reds are lining up, the grays are lining up, but the black and green are not. Well, that's okay. We can make the black and green line up. Boom. There we go. Now they should be stacked right on top of each other. Black, green, black. Uh-oh, the red and gray are not stacked on top of each other. And you never will be able to. You think, maybe I can rotate. Well, if you rotate, guess what? Now the red and black green and black are not going to line up. They are not superimposable. They're different. They're just like your hands. They're mirror images. Just look in the mirror and see this. Except for the freckle or something. Two identical hands, same. How do we know they're not the same? Well, you knew it when you were 1 year old they were not the same, but will they stack on top of each other? If they would, you can just stack them all up. You can't. You're going to have thumb on one side, thumb on the other. Your hands are not superimposable. They're different. Molecules, if they're not superimposable, they're different. Clips, different. No, they're not different. Clips are the same, right? Those are the same. I mean, how are you going to distinguish them? There's no difference. Okay, how do we know that this is going to be the same? Important thing here is plane of symmetry. If something has a plane of symmetry, that is, if you can cut right through it with a plane, and you can cut right through this. If I sawed right through here, I'd have a half a clip on one side and a half a clip on the other, the exact same. It has a plane of symmetry. It actually has two planes of symmetry because I can turn it and come right through here. But all it needs is one. If something has a plane of symmetry, the mirror image is going to be the same. Does my hand have a plane of symmetry? We said last time, no. I cannot slice through it. If I tried to slice right through here, I'd have a thumb on one side, no thumb on the other. If I tried to slice this way, I'd have a palm on one side, knuckle side on the other. There's no plane of symmetry. That tells me the mirror image is going to be different. You've got to trust that. Does this have a plane of symmetry? Does this molecule have a plane of symmetry? Well, if you make a model, again, we did this last time. No, nowhere can you slice right through this. There's no plane of symmetry. Nothing is going to be equal. Since there's no plane of symmetry, we know that the mirror image is going to be different. Indeed, these two are different. Mirror images that are different are called enantiomers. They're different. What's their relationship? Because they're not the same, they're different. The relationship, first off, they're stereoisomers. They have the same connectivity. They're both one bromo, one chloroethane. Same name. Everything connected at the same points, but they're projected differently. The projection is called stereochemistry. They're stereoisomers, but there's two types of stereoisomers. Enantiomers, which are mirror images. These are enantiomers. The other type is called diastereomers. We'll get to that. On the other, the handout you printed, it's got a nice sort of flow diagram of isomers. Isomers, two types of isomers, constitutional and stereo. Constitutional have different connectivity, different names. Of course, all isomers have the same what? Formula. But these have different connectivity. Thus, different names. A lot of times, I mean, one may be an ether, one may be an alcohol. Okay? Stereoisomers, though, have the same connectivity. They only differ in the 3D arrangement of the atoms. Stereoisomers have the same exact name. They're only going to be distinguished by some type of stereochemical descriptor in the front of the name, like cis or trans. But there are two types of stereoisomers. There are enantiomers, which are mirror images that are different. But mirror images that are the same would not be distinguished by anything. They're the same. These are mirror images that are different. These are enantiomers. We'll also see diastereomers. Those are stereoisomers that are not mirror images. Enantiomers have the same exact properties. These two have the same exact boiling point. Because they're essentially the same compound, just sort of everything's reversed, but it's the same though. Same density, same dipole moment. Same refractive index. One quirk of nature though. They differ in how they rotate plane polarized light. Come back to this. Have the same physical properties. Exceptions. Number one, they rotate plane polarized light in equal but opposite directions. Okay? And essentially, Louis Pasteur discovered this when he was working with tartaric acid and salts of tartaric acid back in the 1840s when he was like about 25 years old. Well, actually, he didn't discover the fact that it rotates. He explained why. People knew that things could rotate like this, but they didn't know why. All right. We'll come back and look at 1,1-dibromoethane in a little bit. Let's look at this a little bit. Dextroisomer. That's the enantiomer that rotates plane polarized light to the right. It's also known as the positive direction. That's called dextrorotatory isomer, or D. Okay? Glucose is a chiral molecule. What is chiral? A lot of this is up there in the paragraph, and it's in your textbook, of course. But this is the concept of chirality. When you have this, mirror images that are different. Chirality. Chirality comes from the Greek word for hand, because it's analogous to your hands. This is called chiral. The mirror image is different. So now we have compounds that are chiral, and the idea of chirality. Glucose is a chiral molecule. That is, it has an enantiomer. It has a mirror image that's different. But natural glucose, okay, a lot of times in nature you only find one of the mirror images. All right? And natural glucose actually rotates plane polarized light to the right because it's chiral. And that's why natural glucose is often called dextrose, because it rotates to the right. Okay, if it rotates to the left, it's called levorotatory, or L, and that's the negative direction. And next week in lab, you'll be doing this. You'll be determining the rotation of a compound. And the rotation that, when a compound rotates the PP light, that's called optical activity. Optically active. Okay. We need to look at R and S. Haven't done that yet. The structures. How can we distinguish them? We give them any names. They're both called 1-bromo, 1-chloroethane. But that doesn't help you distinguish between, okay, which is which. What do you want to call this one compared to that one? Well, there's a couple of ways to do that. One is by identifying the configuration at the chiral carbon. And let's talk about that. This is a chiral carbon. The main reason this compound has no symmetry, we said there's no symmetry. That's why the mirror image is different. It has no symmetry. And by the way, if it has no symmetry, we can call it asymmetric. A meaning like anti-symmetric, non-symmetric. Asymmetric. The main reason it's asymmetric is because it has a chiral carbon. A chiral carbon is an asymmetric carbon. It's the most common site of asymmetry. You can have asymmetric nitrogens and sulfur, maybe less common. We'll begin with carbon. And an asymmetric carbon is typically a tetrahedral carbon that has 4 different groups attached. And that's what we have here. That carbon has 4 different groups attached. That, and nothing. And if 4 different things are arranged in a tetrahedral manner, it's going to lack symmetry. There's no symmetry right here. Okay? Chiral carbon. We need to be able to recognize chiral carbons. Now, if we go back and look at the compound, what is it, 1,1-dibromo? If we change this to that, bromine was, what, red? Let's take off the chlorine and have 2 bromines. Okay? Now, is the carbon chiral? No, now it has 2 bromines. And the simplistic definition, it no longer has 4 different things. So it's no longer chiral. That means it's no longer asymmetric. That means it's now symmetric. And we can see that because if it has 2 bromines, we can now slice right through here. And we'll have 1 bromine on one side and 1 bromine on the other. And we'll be slicing right through a hydrogen, so we'll have a half a hydrogen on one side, half a hydrogen on the other. And right through this CH3, and we'll have a half a CH3 on one side, half a CH3 on the other. So with 2 of the same things attached, we now have a plane of symmetry. And since we have a plane of symmetry, what do we know about its mirror image? If we can find a plane of symmetry like we found in the paperclip, what do we know about its mirror image? If you can find a plane of symmetry, the mirror image is the same thing, and thus you don't have any chirality. A paperclip is not called chiral. Okay, let's make the mirror image. We'll just hold it like that. I'm assuming you can see. If you can't see, just yell and we'll adjust. But the light needs to be off for this. Okay. Are those mirroring each other? Okay. They're mirror images. Everything's got a mirror image. Question is, are they the same or different? Well, I've already kind of answered that because we see a plane of symmetry. That should tell us that the mirror image is the same. Well, let's prove it. Are they the same? If they're the same, they should then superimpose. Blacks line up. That red is lined up. Uh-oh, the red and the gray are not lining up. Well, that's okay, because look at this. Boom, there we go. The reds are lining up, the black is lining up, the gray is lining up. I mean, they're sitting right on top of each other. They're the same. They're superimposed. But we knew that because we know if we can find a plane of symmetry, the mirror image is going to be the same. I call that where's Waldo. If you can find Waldo, the mirror image is the same thing. It's not chiral. This carbon is not chiral. Okay? Important thing about a chiral carbon is it's a site of no symmetry. All right? And we could have, all right, don't mess up your drawing, but we could have all types of stuff over here. Okay? This is a carbon with 2 H's. CH2, CH2, CH2. This carbon is symmetrical because it has 2 H's. Everything's symmetrical. Uh-oh, that one's not. And because of that one, it makes the entire compound asymmetrical. Because you can slice through all of this nice and nice, but at the end there, it doesn't work because you can't slice through that part. One chiral carbon destroys the symmetry of the whole molecule. If a compound has 1 chiral carbon, it's going to be chiral, meaning the mirror image is going to be different. Got to be careful though. If you have multiple chiral carbons with a molecule, it may or may not be chiral. But if it has 1, it's always going to be chiral. It ruins the whole molecule in terms of symmetry. Okay, so enantiomers of 1,1-dibromoethane. No, there's no such thing as enantiomers of that compound. The mirror image is the same thing. Okay, important note. Oh, we've got to do this now. R and S. Chiral carbons thus have two different ways you can arrange groups around them. And that's what we have here. We can arrange them this way or that way. That's the difference. Ultimately, yes, it's mirror image, but the groups are arranged differently. So, what do you want to call this way? It's distinguished by R and S. And that's probably Latin for like rectus or something. It basically means right and left, I think. But let's look at that. How do we do that? Similar to when you do EZ terminology, you first give priorities to the groups on your chiral atom based on atomic number. Highest atomic number on this carbon would be what? Bromine, 1. What's next? Chlorine, 2. Carbon. Yes, that carbon has 3 H's, but we look at the first thing that's bonded to this carbon. Carbon, 3. And then the H would be 4. That's the priorities of the groups on the chiral carbon. Now you look at them, and you look at the first 3 groups. And the convention is with the low priority group in the back, which it is, the 4 group is going back. With it going back, is 1, 2, 3 clockwise or counterclockwise? 1, 2, 3 clockwise. And clockwise is called R. I remember that as right, because the dial is turning to the right. Okay? So we say that this has the R configuration of the groups on the chiral carbon. And guess what? The mirror image of R is always S. Just like the mirror image of my right hand is my left hand. The mirror image gives you the inverted one, the other one. Let's prove it. Is that so-called S, which I believe means sinister in Latin. And sinister was given called left because left-handed people were sinister. I don't know if that's where it came about, but that's my story. Everybody left-handed? You're sinister. I say, look it up. S. Is this S? What's the high priority group? 1, 2, 3. Correct? Same as over here, but they're oriented differently. The low priority group, is it in the back? Yes. With the low priority group in the back, how are the 1, 2, 3? Counterclockwise. Correct? This configuration is S. Because of that, we can now distinguish the two enantiomers using R and S. And we can call this one R, and usually you put this in parentheses, dash. What's the name of this compound again? 1 bromo, 1 chloro, ethane. Guess what the name of this one is? S. Same exact name. The only different, a stereochemical descriptor. These are stereoisomers. Same connectivity as shown by the name, different, in this case, different projection. But they're mirror images, so we call them enantiomers. Mirror images have same properties, except they rotate pp light one way or the other. Kind of a quirk. Okay, we have to be careful. We'll add more to this as we go along. Important note, R and S has nothing to do with D and L. What does D and L refer to?
Rotates plane polarized light.
That's how it rotates the PP light. When you have enantiomers, one of them rotates PP light in one way and one the other way. Which one rotates PP light to the right?
To the right.
I have no idea, and I have not given you the information. This R stands for configuration of that has nothing to do with how it rotates light. Sometimes the R compound may be D, sometimes the R compound may be L. Has nothing to do with each other. They have nothing to do with each other. The D and L comes from experiment. You have to go do the rotation experiment to determine that. R and S comes from structure on the board. Okay. Another difference in enantiomers. There's lots of things to say here. It's an interesting, complex story. The paragraphs up there will build upon it. But in addition to rotating PP light, and the rotation of PP light again is back in the 1800s. I sent you a little short summary of that. That was sort of known, and for a long time, scientists, chemists, organic chemists didn't know why things rotated, etc. Okay. The reason these rotate is because a molecule has a heavy electrical component. It's electrons. And light is electromagnetic radiation. It's got electronic properties. And when the light comes in, it interacts with all these electrons. But here the electrons have a certain arrangement, just like your hand. What if the light comes in and it likes to bend towards the thumb? Well, what if the light comes in and because of the electrons, it likes to go between the thumb and the pointing finger? So it comes in and it sort of veers this way. From my view, it's veering to the left. But what if I have the other compound, which is sort of oriented this way? It's going to come through and it's going to veer to the right as it interacts. The light is interacting with the molecule, but the molecules are reversed. They're mirror images. And so the interaction comes, okay? Light and electrons interact and it can be moved. If you had something that was symmetrical, well then, it's really half is the same on each side. And so the light interaction there's no difference because of the symmetry. And so it's just going to come right through the same. There'll be no bending of the light, no rotating. A symmetrical molecule will not rotate the light. These will, but equal opposite direction. Okay, the other thing that's very important, hugely important, it's a very broad statement, is enantiomers interact with chiral objects differently. But you've also known this since you were 1 year old. Because if you had this glove, it will only go into one hand. Okay? This glove will only go into this hand. It will not go into this one. That's an idea of chiral objects. These are chiral objects. Well, guess what? The glove is also chiral. Because here it's mirror image. These are different. Just like these are different. But let's look at this chiral object. These enantiomers interact with that chiral object differently, don't they? Only my right hand will fit into it. The enantiomer of my right hand interacts with that glove differently. You all know that. That's what we're stating here. From a chemical viewpoint, the application of this is drugs interacting with an enzyme. Sometimes you may have two drugs and they're enantiomers of each other, mirror images that are different. And this one may fit into that chiral enzyme, but that one, the mirror image, will not fit into that chiral enzyme. It's the same thing. Thus, this drug may interact with the enzyme and cure a disease where this one will not do anything. That's a very broad, important statement, number 2. Optical rotation. Let's look at that closer, and let's look at different compounds. Questions? We got everything right. I don't know which of these is D or L. I'm not giving you the information. But let's draw two other compounds, and I'll give you some DNL information. Questions?
When you were reciting R next to the compound, you're talking about how the low priority group was in the back. What happened if it was in the front?
We'll just reverse it. We'll do examples of that. You just reverse it. If we did 1, 2, 3, if it was clockwise but the low priority group was in the front, we'd reverse it to counterclockwise, and that would be our answer. That's easy. The more difficult one is when it's not in the front or the back, but it's in the plane. When the low priority group's in the plane, we're going to have to think a little bit more. Okay, optical rotation for enantiomers of 2-butanol. Okay, 2-butanol is an alcohol. Let's just draw it without any stereochemistry. A lot of times things are drawn with no stereochemistry. They're drawn generically. When we first drew these two enantiomers on the board, I probably drew it generically, and I did not include the stereochemistry. This here is 2-butanol. It's an alcohol with the OH on the 2 carbon. All right, you'll learn alcohol nomenclature in organic 2. All right, does it have a chiral carbon? Yes, right here. That's a chiral carbon. This carbon has 4 different groups on it. It has an oxygen, an OH. It has a methyl. And it has an ethyl. Yes, these are carbons, but they're not the same. Because this carbon's bonded to another one, but that one's not. So it's got to be the entire thing. Ethyl and methyl are not the same. And then what else is on this carbon? Undrawn hydrogen. That's a chiral carbon. And chiral carbons can have 2 different configurations. Either the R or S configuration. Just like hands can have 2 different configurations. If you ever see a third wave of hand, let me know. I'd like to see it. It's going to be a freak of nature. But usually hands have 2 different configurations. Chiral carbons have 2 different configurations. They're called R and S. Let's draw them. Let's get a little bit more specific here. Let's see here. La 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 la. La 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 la. Here we go. Boom, boom, boom. Okay. Let's show the projection. You can only have one or the other. Let's draw this like this. Now we're getting precise here. And the mirror image. Okay. Let's draw it as a mirror image, and then we'll try a little something different. Boom, boom. Are those mirror images? Yes? They are? And let's try a third. Oh, wait a minute. You said there's only 2 different configurations. Okay, well, let's see what's going on. First off, does everybody agree that these are both 2-butanol? Butanol, 2. Yeah, we're just showing some stereochemistry here. It's tetrahedral. 2 in the plane, 1 forward. What's back here? Undrawn hydrogen. What's back there? Undrawn hydrogen, right? Okay, are these the same or different? Well, first off, they are mirror images. They look like it. You should, yeah, check. Same or different? Well, Stephen said if it has 1 chiral carbon, then then game's over. It's going to be symmetry's ruined. So there should be no symmetry here. You can cut right through this. You cut right through that because it has 2 H's. But you can't slice right through that because it has 4 different things attached. There's no symmetry there. All right. What is this RS configuration of this carbon? What's high priority on this carbon? Oxygen's 1. What's 2? Carbon or carbon? Well, just like in the easy nomenclature, if it's both carbons, you have to keep going. And the best way to do this, just like with EZ, is what are the atoms on this carbon? H, H, and H. What are the atoms on this carbon? C, H, and H. And look at the first ones. You list these in high priority. Well, right here's your winner. C beats H. Well, this is an easy take-home. If you have a carbon chain, the longer carbon chain is always going to be the high priority. If you follow it out, you'll always win. This is 2, that's 3, and then the undrawn H is in the back, right? Okay? I'm not going to do that. So what is this RS? Correct, that's R. Now that's the mirror image, everybody agree? So what should that one be?
S.
It should be S, because the mirror image of R is S. Let's prove it. Is it? This is 1. Ethyl's 2. Methyl's 3. H is in the back. So what is this? What's this? That's counterclockwise, right? S. One's R and one's S. What's the one over there? Is this a third one, or is it one of these? Or was this RS? There's only 2 choices, RS. Which one is this? Well, this is 1. This is 2. This is 3. The H is forward here. As drawn, the 1, 2, 3 is what? Clockwise. But since the low priority group is forward, what do we do? What do we do with our answer? We flip it. Clockwise, but the low priority group is coming forward, so this is S. Okay? Low priority group in front. This and this are the same compound. These two are the same. If you named them, they would both be S2-butanol. S2-butanol. All right, both of these are the same. This one would be called what? R2-butanol. This molecule has just been done like this. Here the OH is down here and it's coming forward. It's on this end coming forward. I've just turned it around. Now it's on this side going back. It's just turned around. It's the same compound. But labeling both as S helps show that. Now, as we move forward, we're going to stop drawing things as mirror images. I will start showing enantiomers here and there. Because if you leave the backbone the same, all right, boom, 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 the backbone's the same, meaning we're going to put the OH here. See, with the mirror image, we had to move it up here. But you can get the enantiomer by just reversing the projection. Okay? This is the enantiomer. This is S. Same as drawn over on the right. And that's how we'll do it moving forward. I will not always draw something that looks like a mirror image. But by changing the projection, keeping the backbone the same, just changing the projection, you go into the enantiomer. If it's a chiral carbon. All right? Now, I'll give you some rotation information about these. Alpha in parentheses, that's specific rotation when it's in parentheses. It's been normalized. For S equals 13.5. This is S. So this is positive, we'll say, 13.5 degrees. All right? You've got this on the handout. And this one is negative 13.5. Equal but opposite directions. So which is D? Which is L? Positive would be D. Negative is to the left. That'd be LeVo. Okay? We can also use D and L to distinguish compounds. Okay? You may also see this compound called L-2-butanol. And you may also see this compound called D-2-butanol. If you know the rotation. R refers to the configuration on your paper. L refers to the fact that it rotates to the left. In this case, R goes with L. In other cases, R may go with D. They're not related. But it becomes another type of stereochemical descriptor. R refers to one chiral carbon. Thus far, the molecules we looked at have only had one. If you have multiple chiral carbons, like maybe 10 in a compound, you don't typically use R because you'd have to use like 10 of those. You would have to call it. Let's do a little something here. What if we had 5 chiral carbons and it was R, R, S, S, R? What would the mirror image be? The mirror image would be S, S, R, R, S, right? Chiral carbons are reversed in the mirror. These would be enantiomers. But these enantiomers rotate like one way or the other. That means this one maybe is D and this one is L. Compound can have multiple configurations for chiral carbons, but it's only going to be either D or L, because that says a whole. Okay? More later. Now, this terminology, enantiomers are often called DL pairs, because one rotates to the left, one rotates to the right. This is a DL pair. Enantiomers are often called DL pairs. Okay. Let's look at the other handout a little bit. Some daily questions there. Stereochemistry is very important. You know the difference between cellulose and starch? Well, you can eat starch, but you can't eat cellulose. Your body can digest starch, but it can't digest cellulose. If you could eat trees and you'd be no hungry. What's the difference between starch and cellulose? Just stereochemistry. Same connectivity. The difference is it's really a polymer of saccharides, polysaccharides, sugar units. Okay? They're linked with an oxygen bond. But in cellulose, both bonds are equatorial. Huh, what equatorial means, right? But in starch, one bond is equatorial, but the other in the connection is axial. That's just stereochemistry, because the oxygen is connected at the same place, but just the projection of that connection is different. That makes a huge difference, though. Your body can, for some reason, handle starch and digest it, but not cellulose. Stereochemistry is very important. Drugs. Thalidomide. Thalidomide was a drug that was developed to give pregnant women for treat nausea, given in the late 1950s, mainly in Europe, England. It looked like a good drug, but when they started giving it to women, it led to birth defects. Babies being born without any arms or hardly developed arms. The picture here. This is the drug. shown as mirror images. How many chiral carbons in thalidomide? Only one, and it's right here. You could do R and S of that carbon as practice. Okay? These are enantiomers. It turns out that one of them is a good drug. And when they were doing testing, they were only testing one enantiomer. But when they started producing it to be administered, somehow they produced both enantiomers. But the other enantiomer, I don't know which is which, but the other enantiomer turned out to be very toxic, and it led to these birth defects. Perhaps because the toxicity came from one of these fitting into this glove. And when they tested it, it never went in because they only tested this. But when they started giving it, they gave both, and uh-oh, now they gave one that could go into this enzyme. Well, yeah. And maybe in that case, going into that enzyme led to bad things. Okay? It was bad science. They finally figured out what was going on, and I think a nurse figured it out. President Kennedy gave her an award. Most of the birth defects occurred over in Europe, some in the United States. In the end, stereochemistry is very important. Because these mirror images can have different reactivity because enantiomers react with chiral things differently. Look over here. This is an example when you see this on like the Pet Boys commercial, you know? It won't work, and banging on it make it work. You know, some configurations will fit into a receptor where the other configuration will not. But let's look right here. I think this is what I wanted to show you. Okay, we said multiple chiral carbons, but it's only D or L. Look at this huge molecule. It's a drug used to treat prostate cancer. But it has multiple chiral carbons. You've got to be able to find them, recognize them. Sometimes they may be shown generically, but it's still chiral carbon. You can't actually name all the chiral sites. Look at this name. Right? Here's the name. But this name has multiple stereoisomers. They're giving all this. Every site, they're saying SSRSF. Everyone has a precise configuration. The mirror image would be RRS, RSRRSR. But guess what? This compound is either D or L. And for this compound, the rotation is negative 32.9 when done in ethanol. So it's the L enantiomer. You could get rid of all this and just call it L. That's another way to classify that compound. Again, R and S is for each individual chiral carbon. D or L is for a molecule as a whole. There's examples all around for you to be working as practice. Testing yourself, forming questions. Let's see where we're at. Optical activity. By the way, at the very top here, please look at this. Here's more on optical activity. First thing we can say about optical activity is, first off, if the compound's not chiral, it's not going to rotate. Right? This paperclip is not going to rotate light. It's symmetrical. And so any rotation as it's coming through, it ends up getting washed out because it gets done both, because of the symmetry. And you get no net rotation of the light. So we say this is not optically active. A chiral compound, though, is going to be optically active. Okay, question.
on the level of like how active the reacts with light, can you change like the energy state of the molecule with light?
I didn't quite
If
hear.
it rotates, that, I mean, it's probably a stupid question, but
Okay.
if it's more actively affected by light and rotating-wise, does it affect the energy state of the molecule? Like, how something's heat up with light? As it spins faster? No?
I don't know if I can give you a quick answer. I mean, light interacting with the molecule, there's going to be energy there, but how significant is it and how relevant is it? I'm not sure I can tell you anything.
Optical activity of mixtures of enantiomers. All right, we need to be looking at that, including this very important first one, which is a 50-50 mix. 50-50 mix is easy, but a 50-50 mix is not going to be optically active. Because if I have a mix in my hands, as the light's coming through, the light gets bent this way, but guess what? Then it interacts with the other enantiomer, it gets bent back the other way, and you end up with no net rotation. A 50-50 mix gives no net rotation. We call a 50-50 mix a racemic mixture, or racemate, or just racemic. A 50-50 mix is not optically active, just like a non-chiral compound is not optically active. But what if it's a 60-40 mix? You need to learn how to do that, and I want you to be looking at this on your own, pretty much covered on your own. We'll see what type of questions you have on that. We'll be picking back up at below that next time. Fisher projections. Have a good day, guys.